Hello everybody. So, welcome to the first segment of this course on characterization of construction materials. Before we really get into the characterization techniques, we would like to see some basic understanding of different types of construction materials. Okay. So, the idea is to provide you an overview of what you have already learnt in courses before. You may have taken these courses either during your undergraduate program or postgraduate program, depending on whether you are a master's student or a PhD student. In many cases, the kind of detail that you would have covered may not be 100% sufficient to really meet the demands of understanding characterization techniques as applied to these materials, but the exposure that you may have had while doing courses on design, for instance, could have brought you into contact with some of the techniques that are used for actually understanding the properties of these materials. So, I am just going to go over some basics of 4 primary classes of construction materials. We will mainly look at steel, concrete, asphalt and polymers and plastics. Okay. So, why is it important for us to understand structure of materials? Primarily, we need to have a basic idea about the structure and properties, and then once we know this, we can actually select appropriate techniques to look at specific characterization, application of characterization techniques. Okay. So, without further ado, let us talk about Portland cement concrete first, and we will try and see whether we can adopt a material science approach to understanding these materials. So, in that case, if you try to look at Portland cement concrete, it is actually a composite material composed of 2 different phases. The continuous phase in Portland cement concrete is cement paste phase, and the discontinuous phase is the aggregate phase. What do I mean by continuous and discontinuous? Continuous means which is pervading the entire volume. Discontinuous means you have discrete particles of the aggregate which are suspended in the continuous medium of the paste. Okay. Now, you all know very well that aggregate is again composed of fine and coarse aggregate depending upon the size of these materials, and these days you do not just have cement, water and aggregate in concrete, you also have additives, and some of these additives are mineral additives and some are chemical additives. So, of course, mineral additives are like your pozzolanic materials like fly ash or silica fume, or hydraulic materials like slag. You may also sometimes be using inert fillers which are used to actually help in optimizing the particle size distribution of your materials. When you use all these materials in combination, what you need to realize is you are actually looking at different size scales, right. We are talking about particles which may be as small as a few microns. Like silica fume, for instance, the particle size of silica fume is about 0.1 micron, right. On the other hand, you have coarse aggregates which are 20 millimeters or sometimes even more, right. So, you have a complex blend of particles at different size ranges, and because of this there is an inherent heterogeneity associated with concrete. That makes it very difficult to completely design concrete to meet specific demands, but you get an approximate range of properties with some characteristic design methodologies. Okay. So, heterogeneity of concrete is the challenge that we really will come across even with respect to characterization, right. Coming down to the basics of cement itself, you all know that cement is composed of several different types of oxides, the primary ones being calcium oxide, silicon dioxide, aluminum oxide and iron oxide. These are represented as C, S, A and F in cement chemistry notation. Of course, it is a little bit different as compared to regular chemistry, because C would be carbon in regular chemistry, here C is calcium oxide. Okay. There are also other oxides, magnesium, sulfur, sodium and potassium oxide, which are responsible for some of the interesting characteristics that cement has, especially during the hydration process of cement with water. There are other minor oxides which may not have a major bearing on the properties of cement, except for some additional characteristics like color and so on. But for the most part, the properties of cement with respect to its hydration with water are based on these primary oxides that are present in cement. And during the process of manufacture of cement, all of you know that cement is produced out of an intimate blending and burning or calcination of limestone and clay, which leads to the production of these compounds from the oxides. Okay. So, once again using cement chemistry notation, C3S is nothing but tricalcium silicate. So, you have 3 CaO and 1 SiO2 in the formulation of C3S. and C2S is dicalcium silicate or 2CaO SiO2. C3A is tricalcium aluminate or 3CaO Al2O3, and C4AF is tetracalcium aluminoferrite, which is 4CaO Al2O3 Fe2O3. So, again these are approximate chemical formulations for the compounds that are forming out of the clinkering process in cement manufacture. These are not exact chemical formulations like what we know for regular salts, which we deal with in reagent grade chemicals that we used in the laboratory. So, those are very specific formulations, but these are compound formulations that have several different compositions, but the average composition is represented by this formulation. And we all know that during the final process of cement manufacture, gypsum is added to work as a setting regulator, right, and gypsum generally is written as calcium sulphate and with 2 waters of hydration, CS bar H2. So, H2O or water is written as H in cement chemistry notation. So, that is why 2H2O becomes H2. Okay. So, H is not hydrogen, H is water in cement chemistry notation. Of course, we write this just to simplify these chemical formulae, otherwise the compound compositions may become too large. Okay. All right. So, moving on, what are the properties and composition of cement in terms of the percentage of different compounds? Typically, most cements will be very rich in tricalcium silicate C3S. I am talking generally about ordinary Portland cement, right. When you talk about OPC, it will be primarily based on C3S. Typical ordinary Portland cement will at least have greater than 50% of C3S, although the range can be as much as 45 to 60%. Okay. Now, C2S will be typically half of that. Typically half of C3S will be C2S. So, if it is 50% C3S, C2S will be about 25%. So, if you add the silicates together, they will be around 70 to 80% of your cement. Okay. If you take your clinker, 70 to 80% of your clinker will be your silicates, more closer to 80%. Okay. Whereas the aluminates C3A and C4AF, okay, will form about 15 to 20%, and your gypsum will be around 4 to 5%. Okay. Gypsum typically is around 4 to 5%, aluminates are about 15 to 20%, and the remaining nearly 80% is made up of silicates. Okay. So, if you look at ordinary Portland cement today, as it is used in the industry with your 53 and 43 grade cements, the majority of these cements will have C3S contents that are predominant and C2S is much lower. Okay. There is a reason for this, which we will talk about in just a couple of minutes. Okay. In terms of physical characteristics, we all know that cement has a powder specific gravity or solid specific gravity of 3.15. Okay. But when we pack it as a bulk powder inside bags, the density is lower, right. We have about 1.5 to 1.6 as a bulk powder. So, what is the weight of one bag of cement? 50 kg, okay, and this 50 kg corresponds to what?
35 liters.
Okay, 35 liters. It is not exactly 1 cubic foot, but a little bit more than a cubic foot. So, when you use this volumetric batching bucket, which is used on job sites where they do not have weighing facilities, the bucket exactly can hold 1 bag of cement. So, 50 kgs bag is actually designed to fill in that volumetric bucket, so that you only need to measure the volumes of sand and stone when you do the volumetric batching on site. Of course, technically speaking, as far as concrete technology is concerned, we should not recommend volume batching. We need to do weigh batching as much as possible, and design of concrete should be done, and kilogram per cubic meter constituents have to be actually specified in the design. Okay. But in terms of volume batching, you have that bucket exactly fitting with 50 kilograms of cement, and that is the reason why we keep the cement mass at 50 kilograms in a bag. The fineness of cement is typically represented as an air permeability measurement. We call it as the Blaine's fineness, right, or Blaine's specific surface area of 300 to 350 square meters per kilogram. That means, if you take 1 kilogram of cement as a powder, the total surface area of the particles of constituting 1 kilogram will be about 300 square meters, right. So, the finer the cement, the faster it will react, obviously, just like any other chemical reaction. When you reduce the size or you increase the surface area, you cause the reactivity to be higher. Alright, so what happens when cement reacts with water? we call the entire process of cement reaction with water as the hydration of cement, and we all know very well that this hydration process is exothermic. Heat is released and this heat is otherwise known as heat of hydration. And obviously, the quicker the cement reacts, the faster the heat will evolve. And in general, the chemical constitution is important because chemical composition determines how much of each compound is present, and each compound has its own reaction rates. Okay. So, let us look at the compounds specifically. C3A or tricalcium aluminate is responsible for setting an early strength, and it has a very high heat of hydration. C3S again reacts much faster than the other compounds except C3A, of course. C3S also has a very high heat of hydration, and it is generally responsible for the early strength gain of your cement. So, when we deal with concrete, if we are designing concrete to achieve a certain early strength, that early strength will be attributed to the reactions of C3S and C3A. But the long term strength which develops when you continue to cure concrete for a long period of time, it is because of the reaction of C2S. It is responsible for the ultimate strength or long term strength, and because it reacts slowly, its heat of hydration is also lower. Okay. So, generally the finer the cement, the faster will be the rate of heat development and quicker will be your setting and strength gain. That is quite intuitive because again you have reduced the size and increased the surface area. You keep more surfaces available for the reaction, because of which your heat development also increases. Okay. But what are the compounds that these form upon hydration? The primary compound that forms upon hydration is calcium silicate hydrate, CSH, otherwise it is called as. Once again, CSH is only an approximate notation for this compound, complex compound, that is calcium silicate hydrate. Generally the calcium to silica ratio in CSH, calcium to silica ratio is typically about 1.5 to 2. Okay. Now, this ratio depends on many factors, we are not going to go into depth to discuss those right here, but then the variation in compound composition of CSH can be quite extensive, especially when you are talking about binders which also incorporate supplementary cementing materials like fly ash or slag. When you mix these with the cement, you may actually get much different varieties of CSH that are actually getting formed in your system. But for CSH that is formed with ordinary Portland cement, typically the calcium to silica ratio is of the order of 1.5 to 2, closer to 2 actually, and slightly away from 1.5, more closer to 2, right. But then CSH is the phase that is almost gel like in appearance. Why do we say it is like a gel? It is not having a very definite crystalline structure, okay. It has got a sheet like structure which seems to actually stretch over a very long range. So, although the size of CSH is quite small, the agglomerations can actually be a few microns in size. Okay. But if you think about CSH individually, the sheets of CSH indicate a very high surface area for the material. So, if you were to do surface area application or determination techniques for CSH, you will find that the actual surface area exhibited by CSH is of the order of 100,000 or 200,000 square meters per kilogram. And this is forming out of a material like C3S or C2S, which has a fineness of how much? We just discussed that, about 300 to 350 square meters per kilogram. Okay. So, you are forming a completely different compound from the hydration of the cementitious compounds C3S and C2S. Okay. We will talk a little bit more about that when we get to the assessment of surface area characteristics towards the middle part of this course, which will be through this BET technique. Okay. The other compound that forms in large quantities is calcium hydroxide. Of course, it is susceptible to chemical attack, but it has a very important role to play in the concrete because it regulates the alkalinity of the concrete. Okay. Calcium hydroxide regulates the alkalinity of the concrete, and that is why it is extremely important for this compound to be present in the hydrated mixture. Okay. And then you have the calcium sulfoaluminates, which are forming out of the reaction of your calcium aluminates with the gypsum that is added as a set regulator, and that these are responsible for the early stiffening of the concrete, like the formation of ettringite particularly as a phase in the beginning right after the reaction of your C3A with gypsum leads to the formation of ettringite, and this ettringite forms in the shape of needles and essentially causes the stiffening of your early hydration product. Okay. but otherwise the overall volume of these constituents, if you think about it, about 60% would be calcium silicate hydrate, 20% may be about calcium hydroxide, and the remaining 20% will be a mixture of your ettringite, other forms of aluminosulfates like AFM, or AFM is also called aluminoferrite monosulfate. Essentially, it is another form of ettringite which is sulfate deficient. Okay, it has got more alumina, less sulfur. Okay. So, you have ettringite monosulfate, and you may also have other calcium aluminate hydrate products which are forming out of the reaction of the aluminates directly with the water. Okay. But the initial formation will be for the sulfur aluminates. If the gypsum is not added to the cement, these calcium aluminate hydrates form very early during your cement hydration process and lead to a condition which we call as flash set. Okay, that is called flash set. When no gypsum is present, the aluminates hydrate rapidly to form calcium aluminate hydrate, leading to flash setting of your cement. Okay, that is what we want to avoid. That is why we add gypsum, and because gypsum is added, the first reactions end up forming calcium sulfur aluminates like ettringite, which are slowly converted to sulfate deficient forms like monosulfate. But apart from that, you still have the formation of calcium aluminate hydrates later on in the hydration process. So, this is your overall composition of the hydrated cement paste: CSH for the most part, calcium hydroxide to some extent, and then calcium sulfur aluminates and calcium aluminate hydrates form the rest of the system. Okay. Now, that is as far as cement is concerned, but on the other hand you have aggregates, right. Aggregates are mostly considered to be the inert phase that we add in the concrete. In most cases that is true, but in some cases you may also be sourcing aggregates from volcanic sources, which may lead to some reactivity in the aggregate itself. Okay, but then we are not looking at that in detail here. But in general, when we get a sample of aggregate for use in concrete, we test several properties of this aggregate, including crushing strength, modulus of elasticity, hardness, impact and crushing resistance, specific gravity, gradation, bulking, soundness and presence of impurities. All these are important characteristic tests that we perform on aggregate samples, because these lend themselves to specific characteristics in the concrete. So, aggregates, although they are inert, they are responsible for actually filling up the volume of the concrete and giving it dimensional stability. So, aggregates give concrete its dimensional stability. What gives concrete the strength? What is responsible for the strength of the concrete? Yeah, it is the binding of the aggregate by the paste, right. It is the bond then forms with the paste in the aggregate. So, essentially the strength of the concrete is contributed more by the paste system. That is why when we want to increase the strength, we want to reduce the water to cement ratio and make the paste stronger. Okay. The porosity of the paste depends on the water to cement ratio. The lower the water cement ratio, lower the porosity and higher the strength of the concrete. Okay. The aggregates are responsible primarily for keeping the volume of the concrete intact or dimensional stability. However, if you manage to get very good gradation of the aggregate and pack the components of the aggregate well together, they will obviously also contribute to the strength of the concrete. Because now when you pack the aggregates well, you have very little space available that you need to fill up with your cement paste and make the overall voids or porosity in the concrete to be much lesser than otherwise. Okay. So, the primary agent responsible for the strength is the paste and how it binds the aggregate together. The aggregate itself is primarily responsible for dimensional stability, and good packing of the aggregate enables the design of a higher strength concrete mix than if you do not do a good packing of the aggregate. Okay. So, please remember that very carefully. Now, apart from cement, water and aggregate, we also use admixtures commonly in today's concrete, and these can be classified into two types. You have chemical admixtures and mineral admixtures. Now, chemical admixtures are added typically to enhance some characteristics of the concrete which would otherwise not be possible by simply adding cement and water. Okay. Some of these are air entraining chemicals, you have set controllers, water reducers, and sometimes you have specialty admixtures that are used for very specific situations. Okay. For example, there are some chemicals that may be added to the concrete to prevent freezing when it is very cold. Okay. So, that is important because otherwise if the water turns to ice, you will not get the reaction between water and cement leading to hydration. Okay. So, antifreeze chemicals are one examples of specialty admixtures. So, any chemical additive to the concrete during the process of mixing the concrete is called a chemical admixture. Okay. So, the most common class of chemical admixtures that we deal with almost on a day to day basis is water reducing chemicals. And as the name implies, a water reducer means something that reduces the amount of water to achieve a same degree of workability in the concrete. Okay. And those are the most commonly used chemicals in concrete. If you need resistance to freezing and thawing, you probably would want to put in air into the concrete, and that can be obtained with the help of air entraining chemicals. And of course, if you want to conduct, if you want to extend the workability life of your concrete, you want to use something like a retarder. If you want to shorten the period of strength gain, you would want to use an accelerator. So, those are set controlling chemicals that are also used in specific situations. You will not be using them as often as you use the water reducing chemicals. So, water reducers are the most significant from the point of view of chemical admixtures. They are probably used almost in every concrete that we use today in construction. On the other side, we have mineral additives, and these could be reactive or unreactive. Okay. The reactive mineral additives are basically byproducts or waste products from other industries. For example, fly ash is from the burning of coal in thermal power plants. Okay. And this fly ash has siliceous and calcareous impurities that may lead to additional reactions apart from your cement itself. And the most important reaction that takes place in this system is the pozzolanic reaction. And that basically involves the reactive silica from pozzolans like fly ash, silica fume or metakaolin or rhesus ash or volcanic ash, which combines with calcium hydroxide that is produced during cement hydration to form additional calcium silicate hydrate. Okay. Now, of course, calcium silicate hydrate we talked about is the primary binding component of your cement paste, which is responsible primarily for the strength of your paste. Okay. Now, the CSH additionally getting formed from pozzolanic reaction will contribute more to the binding process, although the form of the CSH may be quite different, and this will be something that will be explained to you when we actually look at the specific techniques of characterization. We can actually start picking out CSH that is of different types and of different compositions when you actually substitute cement with mineral additives. Okay. Slag is also listed as an admixture, but actually it is a cement, it is a hydraulic cement. What do you mean by that? That means it will react with water on its own. Slag will react with water on its own and lead to cementing reactions that form compounds similar to CSH and calcium aluminate hydrates. Okay. Slag is not really a pozzolan, it is actually a hydraulic cement, but it is bunched under the same category of mineral admixtures. And commonly you find that people use fillers like quartz and limestone powder to enhance the particle gradation of your aggregates in concrete, and also to get more fines inside to impart certain special characteristics. Okay. So, inert fillers can also be used, but now we know that there is sufficient research to also show that limestone is not necessarily inert. Some part of it actually does react with aluminates to lead to some interesting chemistries in your system. I will give some examples later when we talk about hydration processes that are detected through scanning electron microscopy, for instance, where you will see how the microstructure actually changes significantly when you use a combination of these mineral additives and fillers.